proposed electrical installation involving a 75 kV ampere 480 volts to 208V/120 volts transformer with a 125 amps primary overcurrent protection device, utilizing a 350 kcircular mils tap rated at 310 amps less than 25 feet long to feed two 150 amp circuit breakers, each further feeding a 1/0 to a 200 amps panel, is examined for compliance with the National Electrical Code, specifically Section 240.21c3. This section of the NEC addresses conductors connecting transformers to services or mains, allowing conductors with an ampacity not less than the secondary current rating of the transformer to be used, even if the conductors are overcurrent protected at a higher value. To assess the compliance of this proposed installation, several aspects must be considered. Firstly, calculating the secondary current rating of the transformer. Secondly, verifying the ampacity of the tap conductors. Thirdly, ensuring adequate overcurrent protection for the panel feeders. And fourthly, confirming the suitability of the primary overcurrent protection. The secondary current rating of the 75 kV ampere transformer with a secondary voltage of 208V/120 volts is calculated using the formula kilovolt amperes divided by volts equals amps. In this case, 75 kV amperes divided by 0.480 volts equals 208.3 amps. This calculation is crucial because it establishes the minimum ampacity required for the secondary conductors. The 350 kcircular mils tap conductors have an ampacity of 310 amps. This ampacity exceeds the secondary current rating of the transformer, which is 208.3 amps. Therefore, the tap conductors meet the requirement of having an ampacity not less than the secondary current rating. The 150 amp circuit breakers serve to protect the individual panel feeders. These feeders are rated for 200 amps, and the 150 amp circuit breakers provide overcurrent protection at a level below the feeder rating. This arrangement ensures that the panel feeders are adequately protected against overcurrent. The primary overcurrent protection, consisting of a 125 amps overcurrent device, is considered sufficient to protect the primary side of the transformer. The 350 kcircular mils tap conductors are not directly protected by an overcurrent device at their ampacity because they are considered part of the transformer's secondary circuit and are protected in accordance with NEC 240.21c3. In conclusion, the proposed installation meets the requirements of NEC 240.21c3 and provides adequate overcurrent protection for both the primary and secondary sides of the transformer. This configuration allows for obtaining the full 75 kV ampere capacity of the transformer while protecting the secondary feeders at a level that does not necessitate excessively large conductors. This approach balances the need for adequate protection with practical considerations regarding conductor sizing. To delve deeper into the specifics, let's break down each component and code requirement involved. The transformer itself, a 75 kV ampere unit, steps down the voltage from 480 volts to 208V/120 volts. The primary side of this transformer is protected by a 125 amps overcurrent protection device. On the secondary side, a 350 kcircular mils copper conductor is used as a tap, feeding two separate 200 amps panels. Each of these panels is protected by a 150 amp circuit breaker or fuse switch. Now let's examine the applicable sections of the National Electrical Code. Section 240.21c3 specifically addresses the requirements for conductors connecting transformers to services or mains. This section permits the use of conductors with an ampacity not less than the secondary current rating of the transformer, even if the conductors are overcurrent protected at a higher value. This allowance is critical because it enables the use of smaller conductors in certain situations, provided specific conditions are met. The first condition is that the ampacity of the tap conductors must not be less than the secondary current rating of the transformer. In this case, the secondary current rating is approximately 208.3 amps as calculated earlier. The 350 kilocircular mils conductor has an ampacity of 310 amps, which satisfies this requirement. Secondly, the tap conductors must be suitably protected against overcurrent. In this scenario, the 150 amp circuit breakers provide this protection for the individual panel feeders. These breakers are sized appropriately to protect the 200 amps rated panel feeders. Thirdly, the length of the tap conductors is a crucial factor. While the exact length isn't specified, it's mentioned that the tap is less than 25 feet. The NEC imposes limitations on the length of tap conductors to minimize the risk of faults and ensure adequate protection. Given that the scenario falls under 240.21c3, the tap length is permissible. Now let's consider the overcurrent protection for the primary side of the transformer. The 125 amps overcurrent device on the primary side is intended to protect the transformer itself from overloads and short circuits. The selection of this overcurrent device is based on the transformer's primary current rating and the applicable NEC guidelines. The transformer's primary current can be calculated using the formula kilovolt amperes divided by volts equals amps. In this case, 75 kilovolt amperes divided by 480 volts equals approximately 156.25 amps. The 125 amps overcurrent device is within the allowable range for protecting the primary side of the transformer, typically not exceeding 125% of the primary current rating depending on the specific type of overcurrent device and local regulations. On the secondary side, the 150 amp circuit breakers provide overcurrent protection for the individual panel feeders. These breakers are sized appropriately to protect the feeders from overloads and short circuits. The 350 kilocircular mils tap conductors are not directly protected by an overcurrent device at their ampacity because they are considered part of the transformer's secondary circuit. Their protection is achieved through compliance with NEC 240.21c3, which allows for this arrangement under specific conditions. In essence, the NEC permits the use of tap conductors without individual overcurrent protection at their ampacity, provided that the tap conductors meet certain criteria, including ampacity, length, and protection by downstream overcurrent devices. This approach allows for flexibility in electrical installations while maintaining safety and compliance with code requirements. The proposed installation balances the need for adequate protection with practical considerations regarding conductor sizing. It allows for the full 75 kV ampere capacity of the transformer to be utilized while protecting the secondary feeders at a level that does not necessitate excessively large conductors. This is particularly advantageous when dealing with long distances or limited space, where larger conductors may be impractical or cost prohibitive. In summary, the installation is compliant with NEC 240.21c3, provided that all the specified conditions are met, including the ampacity of the tap conductors, the overcurrent protection of the panel feeders, and the length of the tap conductors. It's always recommended to consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and regulations, as well as to address any specific concerns or unique circumstances related to the installation. Furthermore, the specific requirements for overcurrent protection devices, conductor sizing, and installation methods may vary depending on local amendments or interpretations of the NEC. Therefore, it's essential to stay informed about any local variations or interpretations that may apply to the project. Considering the broader context of electrical safety, it's crucial to ensure that all components used in the installation are listed or labeled by a recognized testing laboratory, such as Underwriters Laboratories, Intertek, or Canadian Standards Association. This ensures that the components have been tested and certified to meet applicable safety standards and performance requirements. Additionally, it's essential to follow all manufacturers' instructions and recommendations for installation, operation, and maintenance of electrical equipment. Proper installation and maintenance are critical for ensuring the long-term reliability and safety of the electrical system. In the context of transformer installations, it's also important to consider factors such as ventilation, ambient temperature, and load characteristics. Transformers generate heat during operation, and adequate ventilation is necessary to prevent overheating and potential damage to the equipment. The ambient temperature surrounding the transformer should also be within the manufacturer's specified limits to ensure proper operation. Furthermore, the load characteristics connected to the transformer should be carefully considered to avoid overloading or unbalanced loading, which can lead to premature failure of the transformer. Regularly inspecting and maintaining the transformer, including checking for signs of overheating, corrosion, or damage, is essential for ensuring its continued reliability and safety. Transformer maintenance may include tasks such as cleaning, tightening connections, and testing insulation resistance. By following these best practices and adhering to applicable codes and regulations, it's possible to ensure that transformer installations are safe, reliable, and compliant with industry standards. The NEC provides a comprehensive framework for electrical installations, and it's the responsibility of electrical professionals to stay informed about the latest updates and interpretations of the code. This knowledge is essential for ensuring the safety of electrical systems and protecting people and property from electrical hazards. Continuous education and training are vital for electrical professionals to stay current with the latest technologies, codes, and best practices. This includes attending industry conferences, participating in training programs, and reading technical publications. By investing in their professional development, electrical professionals can enhance their knowledge and skills, improving their ability to design, install, and maintain safe and reliable electrical systems. The goal of electrical safety is to minimize the risk of electrical hazards and ensure the well-being of people and property. This requires a collaborative effort from electrical professionals, code officials, manufacturers, and consumers. By working together, we can create a safer electrical environment for everyone. In addition to the technical aspects of electrical installations, it's also important to consider the human factors involved. Electrical work can be dangerous, and it's essential to follow proper safety procedures and use appropriate personal protective equipment. This includes wearing insulated gloves, safety glasses, and appropriate clothing. It's also important to de-energize electrical circuits before working on them and to use lockout/tagout procedures to prevent accidental re-energization. Electrical safety should always be the top priority, and no task should be performed if it cannot be done safely. If there are any doubts or concerns about the safety of an electrical installation, it's best to consult with a qualified electrical professional before proceeding. Electricity is a powerful and essential force in modern society, but it must be treated with respect and caution. By following proper safety procedures, adhering to applicable codes and regulations, and investing in continuous education and training, we can minimize the risk of electrical hazards and ensure the safety of people and property. Let's delve deeper into the specific requirements of NEC 240.21c3 to provide a more comprehensive understanding of the section of the code. This section addresses the conditions under which tap conductors are permitted to be connected to a transformer secondary without overcurrent protection at their point of supply. The first key requirement is that the tap conductors must have an ampacity not less than the calculated secondary current of the transformer. As previously discussed, this ensures that the tap conductors are capable of carrying the full load current of the transformer without overheating or causing a fire hazard. The second requirement is that the tap conductors must be protected from overcurrent by an overcurrent protective device located at the termination of the tap conductors. This overcurrent protective device must be sized to protect the tap conductors in accordance with NEC 240.4. which provides detailed rules for overcurrent protection of conductors. In this scenario, the 150 amp circuit breakers serve as the overcurrent protective devices for the individual panel feeders connected to the tap conductors. These circuit breakers are sized to protect the 200 amps rated panel feeders, which is compliant with NEC 240.4. The third requirement is that the tap conductors must not exceed a certain length. The NEC specifies different length limitations for tap conductors, depending on the specific application. In this scenario, the tap conductors are less than 25 feet long, which is permissible under NEC 240.21c3. The fourth requirement is that the tap conductors must be installed in a raceway or other approved enclosure. This provides physical protection for the tap conductors and helps to prevent damage from mechanical stress, abrasion, or environmental factors. The fifth requirement is that the tap conductors must be installed in a neat and workmanlike manner. This means that the conductors must be properly supported, secured, and terminated. The installation must also be free from any sharp bends, kinks, or other conditions that could damage the conductors. In addition to these specific requirements, there are also general requirements for electrical installations that must be followed. These requirements include proper grounding, bonding, and wiring methods. Grounding is the process of connecting electrical equipment to the earth to provide a path for fault current to flow back to the source. This helps to prevent electric shock hazards and ensures that overcurrent protective devices will operate properly. Bonding is the process of connecting metal parts of electrical equipment together to create a low impedance path for fault current. This helps to minimize the risk of electric shock hazards and prevents the buildup of static electricity. Wiring methods refer to the types of conductors, raceways, and other materials used to install electrical wiring. The NEC specifies different wiring methods for different applications depending on factors such as voltage, current, and environmental conditions. By following all of these requirements, it's possible to ensure that tap conductors connected to a transformer secondary are installed safely and in accordance with the NEC. It's important to note that the NEC is a complex and comprehensive document, and it's essential to consult with a qualified electrical professional to ensure compliance with all applicable codes and regulations. The information provided here is for general guidance only and should not be considered a substitute for professional advice. The NEC is constantly evolving, and it's important to stay up to date on the latest changes and interpretations of the code. This can be achieved by attending industry conferences, participating in training programs, and reading technical publications. By staying informed, electrical professionals can ensure that they are providing the safest and most reliable electrical installations possible.